excited. Okay. So question number 3 said the same kind of lab, except that he was using fish heads because he's the Swedish chef and that's what he does. If you guys have ever seen this, have you seen the Swedish chef? Do you know him? He goes bork, bork, bork. Then he throws fish heads in the air and makes a huge mess. It's really funny. Someday, Carrie Ann, I'm telling you, it's going to be great. So it's the same kind of problem like all of these other problems were. So there's an inclined plane, but this time he has a fish head, so it's like this. It's the same deal. So you've got all the same forces and all of that. We know the mass, and we know what mu is, but we want to find theta, right? So if we go back up here, just because I'm just going to look at this to be quick, mu is FF over Fn. FF is mg sine theta. Fn is mg cosine theta. So the game here is we've got mg sine theta over mg cosine theta. And just a hint for future reference as you go through life, if there's a hint or a note or something in parentheses or like, you know, it usually is helpful. And I don't mean that in like a snarky way, but just in a like, that's why this is here, right? Some of you know this because in math you've already done this. Some of you haven't, and that's okay too. That's why I put it here. So the mg's actually cancel out. Here's the secret. You didn't have to take the mass of anything in order to find your mu's, right? It really is just mu is equal to the tangent of theta. So to find theta, it's just going to be tan inverse of mu. Do you see what I'm saying? Okay. So I'm going to give you just a moment. If you need to finish that up, you can. And I asked you to get a textbook, but if you haven't done that yet, do that. I'm going to give you 90 seconds. Oh, man, just 90 seconds to make everything happen. And the basket's up there to put the labs in. Go, go, go. I'm open for any of them. So why don't you take a look through your homework right now, figure out what questions you'll have. Raise your hand with questions. I'm going to make a big list, and then we'll work through them. Does that sound good? All right, so I'm going to just write this down so I don't forget and so people know. Chapter 4, homework, questions. All right, Anna, what you got? 53, she says. Madison?
52.
52. Yeah. 23. Other questions on the homework from chapter 4? So whether you have the homework done or not, I would encourage you to have paper and a pencil out, right? If you have the homework done, I'd have your homework out so you can, if you need to make any corrections or whatever, that's good, okay? If you didn't do it or you didn't get it stamped or whatever, this is a good time to write at least these ones down. So you've got something started, okay? Also, before we go through this, I want to just friendly reminder, if your grade is not where you want it to be, I do accept corrections and late stuff for half credit. It's not as good as full credit, but it's a whole lot better than a 0, okay? Spring break is a really good time to take a day and just get it done so you don't have to worry about it, so it's not hanging over your head, and so you're not freaking out about your grade, and so your mom and dad aren't freaking out about your grade, right? Okay, so do it. Bring me in a pile of stuff. We'll put it in the late bin. I'll get it graded. It'll be great. Okay? All right. Let's start with 23. So I'm looking at page 152. Oh, yes. Do you remember when we were doing projectile motion? And you're like, yeah. And I told you that the acceleration in the y direction would always be negative 9.8, and the acceleration in the x direction would always be 0, except one time. This is the one time. This is the one case this semester when it's not going to be the case. Let's take a look at what's going on. So it looks like an average normal projectile motion problem in a lot of ways. A 3-kilogram ball is dropped from the roof of a building that's 176.4 meters high. Okay, so I can do that. 176.4 meters above the ground. 0.4. So there is my object. It says while the ball is falling to the earth, because it's dropped, right? So where should it go? Straight down, right? That's everything else that we've dropped has gone straight down, right? But it says while it's falling, oh, there's a horizontal wind. That's exerting a force on it, right? That's kind of interesting. The force is 12 newtons. I'm going to put it that way just because my building is in the way, so the ball can't go the other way. Where is the ball going to go? Can you draw a trajectory for that ball for me? What's it going to look like? Draw it with your pencil or finger in the air. Is it going to go straight down? Right? It's going to have some sort of like parabolic something, right? So this is really like a projectile motion problem. So whenever you are approaching a projectile motion problem, writing that list of givens is always a good thing, right? So let's do that. So dx, vx, that's the initial v, right? Ax, dy, vy, ay, and t. Tell me something I know. Zach?
Changing y is negative 176.4 meters.
Yay. Why is it negative?
Because it's going down.
Is that okay? All right. Taking a look at the problem. What else do you know?
AY is negative 9.84 meters per second squared.
Because it always is, right? Yeah. What else do you know? Anything else? Why don't you talk to your table mates? I'll give you 45 seconds to talk to them. See if you can come up with anything else that you might know. Go, go, go. Talk to your table. Go, go, go. Noise, noise, noise. Okay. What did you come up with? What's something else you know? You had some I heard some good conversation there. Tim, what do you know?
The acceleration in the x direction is 4.
Is 4.
4 meters per second squared.
Did anybody else come up with that?
Yeah.
Yeah? Why? Why 4?
Because acceleration equals force divided by mass.
Okay, let's write that down. Acceleration equals F net in the x direction. We're talking about just in the x direction divided by m. Is everybody okay with that statement? We came up with that a while ago, right? That's like Newton's first and second law. That's like the equation part of it. We know the force is 12 newtons. We know the mass of the object is 3 kilograms. It's kind of a heavy ball. Honestly, that's pretty massive. But 12 divided by 3 is a really nice round 4. Is that okay? Okay. Cool. What else do you know? Anything else? You already told me something. I want to share the fun. I heard lots of good conversations, so there's got to be something else that you know. Do you need another 15 seconds to talk? Madison?
Is there going to be a 0 value for one of those?
There'd probably be a 0 in there. Where do you want to put a 0? Just like arbitrary throw zeros in?
No, dx, is that going anywhere?
Well,
I mean,
draw
I
the
think
trajectory
it's
for me.
The dx going in?
I don't know. What do you think? Is Vx something?
Yes.
Let's take a look, friends. I've got a 3 kilogram ball. I'm going to drop it from 176.4 6.4 meters. There's a wind. The wind's coming this way. I don't think I have bad breath, so I'm not that good. But right, tell me about its velocity. At the beginning, right? These are initial velocities.
Well, if it has acceleration, then it has to have no velocity, right?
What'd you say?
It doesn't.
It doesn't. She says it does, you say it doesn't. Why? Why do you say it has to have a velocity?
Because if it has an acceleration in the x direction, it has
Uh-huh.
to have a speed, right?
Well, I don't know. What do you think, John?
But didn't it say it was hold it and then the wind, you let it go? So I don't know how it's going in this head.
So so let's watch. If I throw the frog like this, does he have initial velocity in the x direction? Yes, because let's just think about this from a non-projectile motion, but from a forces perspective. Right now, what's his velocity? 0. I apply a what? A force, which causes him to accelerate, and so he's accelerating in this time, right? Like while I'm pushing on him. As soon as I let go, then there's no more force, right? So then he's moving at whatever speed he was moving at, blah, blah. If I just let him go, what's his velocity going to be at the beginning? 0. Even if there's a force acting. Is there a force acting on the frog in the y direction? Is there an acceleration in the y direction? Yeah. Does his velocity have to be something in the y direction to start? No. They're separate. So at some point, I mean, the one thing you know is that if there is acceleration, then the velocity isn't going to be constant, right? It's going to be changing. But at the beginning, it can be 0. Does that make sense?
Oh, is it 0 right now?
Well, I'm asking. I don't know. I mean, I do know, but I
My
don't want to tell
notes
you.
say this right here. With Vy equals 0.
So Madison's asserting that Vy is 0. What do you guys think? Do you agree with her?
Yes.
Okay.
Agreed.
What about Vx?
No, not 0.
Lots of zeros.
We have to find Vx.
Yeah, I didn't know. It's given.
Okay, hold on. Vy we think is 0. That's what you're telling me? Ivy, what's up, bud?
Yeah, we end up finding speed anyway.
I would guess because you put the arrow going that way. Is it 12?
No, that's just a force.
Okay.
That's not an initial velocity vector. That's kind of not. I wasn't intending to confuse you. Is what I'm trying to say. Does it have any initial velocity in the x direction to start? Rowan's shaking her head no. Kristen, what do you think? Right, yeah. So it starts off here. The wind then starts to push it, but it starts with a velocity of 0. Oops, I need an equal sign in there. All right, so we didn't actually even look at the problem. I just kind of figured that would be a good way to start it. It says, how long does it take? So what are we looking for there? Time. That's going to be easy, right? We can just use the
equation.
big equation with all the fun. Boom. Use the y stuff and life is good. Part B says, how far from the building does it fall? Or does it hit the ground? What are you solving for there? Dx, right? Can you solve for dx at that point? Yeah, because you know the time, so life is good. So then you're just going to use the time and the x stuff to solve for dx. And then part C, it does say what is its speed when it hits the ground. So here's the thing. If we draw the trajectory of this thing, does it make sense it's going to go like this? Yeah? At the very end, right when it hits the ground, the velocity vector looks like that. Is that okay? So the velocity vector is going down at a funny angle. They want to know what that velocity is. They say speed because they don't care about the direction, which is nice. But what you really have to do, I'm going to just make that velocity vector really, really big so I can see it better. I need to figure out how fast it's going in the y direction and how fast it's going in the x direction. Are you with me there? And then use the nice, wonderful Pythagorean theorem. Ah, come on, silly thing. So this is Vx. This is Vy. That's a right angle. And these are the finals. So you'll need to calculate Vy final and Vx final. Can you do that? Do you know what they are offhand? Like, can you just, do they exist up there anywhere?
0.
Is it 0?
That's what it's saying.
Is its velocity 0 in the x or in the y?
Well, it can't be starts off with 0, but then it changes.
Right. These are both initial.
One has to accelerate,
But what'd you say?
but then it starts to accelerate.
Right. So you need an equation that has initial velocity, final velocity, acceleration, and time in it. Do you have an equation that looks like that? Yeah. Like the definition of acceleration, right? Yeah, so I think it's like what, VF is equal to VI plus AT.
Yeah, that.
Yeah, that.
Oh,
Does that get you far enough in that problem? Is that okay? I'm going to keep going, so put a little star by that, write those notes down. After I get through these problems, then I'm going to just give you some time to work. You can work on these problems, or you can work on the problem set problems. Does that sound okay? So I'm going to keep going so that I can get through this stuff, so that if people are done with this, they don't have to just wait on us. Okay? But you can certainly come back to that one. Let's take a look at 52 and 53. And if you want me to go back to that later, I'm very happy to as well. 52 and 53. So now we're on page 154. It says a boat moves through the water with two forces acting on it. Okay. Let's draw this picture. I like to draw pictures. It helps me to see. I would encourage you to draw pictures too. I think it'll help. So here's my boat. It moves through the water with two forces. One of them is pushing forward with 2,100 newtons of force by the motor. So that's the force of the motor on the boat. And then I've also got a force backwards, right? A resistive force. So a force, oops, that should be straight line. Of 1,800 newtons. Force of the water on the boat. The first thing says, what is the acceleration? So, how do we find acceleration? Say that.
F net equals m times
Yeah. F net equals ma, right? Can you find the net force? Yeah, you've got a positive 2,100 and a negative 1,800. Subtract that. Is that okay? Okay? And then divide by mass, and that'll give you the acceleration. Is that okay with people?
So you subtract those two.
Yep, because so your F net is going to be the force of the motor plus the force of the water equals ma. But the motor goes in one direction and the water goes in the other direction, so it's really Fm minus Fw is equal to ma. Part B says if it starts at rest, so that means initial velocity is 0, right? How far will it move in 12 seconds? So that's a time of 12. It wants to know how far it's going to go. What does that mean? Displacement, change in x. And, oh wait, in part A you found acceleration. So this is from part A. Hey, it's the same one. I told you were going to love it. Told you better get used to it because it's going to be there forever. Right? And then, so this is part B. And this was part A. And then part C. What will its speed be? So what are they wanting to know? Final velocity. You know its initial velocity. You know its time. You know the acceleration because you found that in part A. So you can do that one too. What's up?
For the force, is it mass divided by, or for the acceleration, is it mass divided by force or force divided by mass?
We'll take a look. What does it say? If you're going to solve this right here, to get A all by itself, what are you going to do?
Divided by
Divide by what?
mass.
Yeah.
Yeah.
Yeah. You are correct. Questions on this one? Does that get you where you need to go on that one? Is that okay? All right, and then the last one. Oh, this is the one with the sledder? Yeah, we don't want to talk about this anymore because it's spring, right? It's not winter. But that's okay. It's still a good problem. 53 is not a hard problem, but there's a lot of stuff in the problem. Okay? So let me see if I can help you kind of like rip it apart and figure out what's going on. So you've got a girl coasting down a hill on a sled. Whee! Did you guys have good sledding? Did you get lots of sledding in this winter? No? Oh. What did you say?
I said totally in the summer.
You go sledding in the summer?
You said summer.
Did I say summer? I meant to say winter. I think my brain is just on summer. Sorry. Did you totally get a lot of good sledding in this winter? Oh. It was too summery? It was like really cold. Oh, true. Okay. All right. Anyway, sorry, I didn't mean to digress too much. Here we go. Shh. So she coasts down the hill. We don't really care about the hill, though. Really what we care about is that right here, at this spot, she's moving with an initial velocity of 7 meters per second. Is that okay? It says the coefficient of friction between the sled's runners and the hard icy snow. So this is not super slick. It's a little bit bumpy. The coefficient of friction is 0.050. So it's still pretty slippery. Just not like, non-existent. Okay? If there is friction, what do you know about her motion? Is she going to keep going at the same speed forever? No. Because if we drew a free body diagram of her, let's just do it because we can. And because we'll need to. What forces are acting on her as she's moving across that hard icy snow? Gravity, the force of the earth, right? On this, I'll just say the sled and the kid all together. There are lots of problems on your problem set. Almost every single one you have to draw a free body diagram. So get used to it now. Get started on it now. Practice it now. I will look for a free body diagram on this problem, and if you don't have one, you won't get it right. So make sure you draw a free body diagram. Besides the earth on the sled, what else you got? Normal force. Where does that one go? Perpendicular to the surface. That means it's going to be up, straight up, right? So that's the force of the ice on the sled, F sub n. This is what I want your free body diagrams to look like, friends. So if it doesn't look like this, start making it look like this. Anything else acting on the little girl on her sled? What's that? How do you know there's friction? Because there's a mu, right? Here's the hint. If there's a coefficient of friction, that probably means there's a force of friction. Where is the force of friction pulling or pushing?
That way.
Which way? That way. So what to the surface? Parallel to the surface. And is it in the direction of motion or opposite the direction of motion? Always opposite the direction of motion. So it's going to be this way, right? So the force, this is again the ice on the sled. That's the force of friction. right, let's keep reading here. The girl and the sled together weigh 645 newtons. So if I'm going to write down 645 newtons, what am I going to write that as equal to? So m times little g, or we can just write it as Fg. It's the force of the earth on the sled and the girl, right? We can put mg in there just to remind us that that's what it is. The question says, how far do they travel before coming to rest? So before coming to rest, that means that the final velocity is 0. And what are we looking for? The distance, how far, like a delta x or something like that? So let's just talk about how to approach this question. Sometimes, this question is this is a tough one. We really need to talk it out. What's your plan of attack going to be? Cry and hide under the table? That's a bad choice. Let's attack it. Let's do it. What are you thinking?
To find the force of friction.
Okay. What's that going to do for us?
I don't know. Just the first human I know.
Seems like a reasonable thing to do. Okay, so I'm not going to do the problem for you, but let's just talk through what. So Ibby is suggesting that we find FF. If we find FF, what's that going to do for us?
We can find the acceleration.
Then we can find, well, how?
Acceleration is force by the mass. So then we can divide 600. Wait. Well, let's find the mass. At some point.
So we need F net to be all the forces. All of them. All together. Then.
Ashley, you were going to say something.
Well, like if you know the force of friction, you can find the F net in the x direction, and which you can also use the force of gravity to find the mass, because you know that. And so then you can find the acceleration using F net over mass equals acceleration.
Okay, so we're going to use Fg to find m. I'm just trying to keep track of what all you said. So you're going to use Fg to find m. Is everybody okay with that? We're going to use, how are we going to find FF? Yeah, we're going to use FF equals mu Fn to find FF. How are we going to find Fn? What's that? How do you know that?
Because the sled's not flying places or sinking into the earth.
So maybe we could say that we could use the F net
Yeah, the F net
in the y direction to find Fn, and then use FF equals mu Fn to find FF, and use FF and m to find A. Is that making sense? And if we do that and we find A, are we done? No, but once we find A, then what? Then you can do the problem. Who said that? That was kind of funny. Yes, you can do, well, then it's an easy kinematics problem, right? Because then you have initial velocity, final velocity, acceleration, and displacement. And that's not hard. Is that okay? Do you have an equation? Probably on your equation sheet, in fact. Yeah. Okay. I think you have a plan. I don't want to do it for you because if I do it for you, then you don't get the lovely experience of doing it yourself. So what I'm going to do right now is to give you some time. I want you to work on this problem first with your partners. If you're done with it, then you don't have to work on it. But if you're not done with it, go ahead and work on this one first. If or when you finish this problem, and the answer is up on the board, you can then either work on other homework questions or you can work on the problem set. Before I release you to go ahead and get started on this, would you all pull the problem set out to take a look at it really quickly for just a moment? I just wanted to draw your attention to a couple of things. Does anybody need a copy of it? Everybody has theirs? Questions number 1, 2, and 3 are really just kinematics and F equals MA questions. Okay? You do not have to write F-net equations, or yeah, you don't, well, you will on number 3. You don't have to draw free body diagrams for those so much, at least for numbers 1 and 2. I would say for 3 through to end, you must have a free body diagram. Start with the free body diagram. Use the free body diagram to write your F-net equations, and that will lead you through towards the end. Numbers 4 and 5, you might just want to write this down so you don't forget, are very similar to the problem where I was walking the frog. Do you remember that? So that's on a horizontal surface, and the force is applied at an angle. It says, when it says downward at an angle, that means I'm pushing down. So as opposed to pulling up, I'm pushing down. And then on the back, numbers 5, 6, and 7, or 5, 7, and 8, because apparently they got numbered weird, whatever. The last 3 questions, whatever numbers they say, mine says 5, 7, and 8 on it for some reason, are incline problems. So these are like the frog sitting on the book or the candy bar sitting on the book. It's the same kind of deal, okay? Number 8 is extra credit. It's not a really hard problem, but it is just a little bit deeper. Does that make sense? Okay. I'm going to collect this on Monday when you get back from spring break. Okay? So this is due on Monday after spring break. Do you have questions right now? Yeah.
You have to do all parts of number 8 to get full credit.
To get full credit, you would.
Yeah.
But like if you just do part A, then you might get a point.
Okay.
Does that make sense? Yeah. All right. So first of all, you're going to finish number 53. Then work on this or on homework. Either way, you should be working on physics for the next 20 minutes. If you're not sitting next to, like if there's nobody next to you because they left or you just want to move around, that's fine with me as long as you're staying focused on physics. Yeah. All right, go, go, go. Ask me lots of questions too. Yeah.